When it comes to thermal conductivity and thermal physical testing, accuracy is everything. These measurements shape innovation in electronics cooling, aerospace materials, battery development, energy storage, and more. But many engineers and researchers new to thermal testing run into the same question. What's the difference between a testing module and a testing method? Understanding this distinction is essential for choosing the right tools and ensuring that the data you collect is meaningful, accurate, and relevant to your application. Thermophysical testing focuses on how materials store, conduct, and respond to heat. These measurements rely heavily on controlled environments, and that's where both testing modules and testing methods come into play. Each serves a different role, and both are necessary for successful thermal testing. Let's start with testing modules. Modules are the physical fixtures, hardware systems, and software calculations that enable a thermophysical test. Think of them as the environment and equipment that make a testing method possible. They include things like sensors, TPS, hot wire, line source, sample chambers and fixtures, and accessories like insulation, test cells, and compression rings. A module helps answer questions like, what geometry does the sample need? How will the sensor interface with that material? What environmental conditions are required? The same testing method can use different modules to work with different materials or configurations. Transient methods apply a short burst of heat and observe the material's response over time. Examples include transient plane source, transient hot wire, laser flash analysis, and transient line source. Advantages include fast measurements, broad material compatibility, and ability to measure multiple properties. Method limitations include sample preparation sensitivity and may require accurate specific heat input. Steady-state methods measure properties under constant heat flow. These include guarded hot plate, heat flow meter, and guarded heat flow meter testing. Advantages include high accuracy for homogeneous materials and direct through thickness thermal resistance. Limitations include longer test times, larger samples, and less suitable for high conductivity materials. A testing method can be prepared with multiple modules depending on the sample. Take the TPS method, for example. It can be paired with a 3D module for bulk materials, a slab module for sheet materials, an anisotropic module for composites, a 1D module for rods. The method defines the science. The module defines how that science is applied. When the wrong module is paired with the right method, issues appear quickly. Poor sensor contact, incorrect constraints, edge effects or heat losses, and misalignment with actual heat flow. Even with a robust method, the wrong module can compromise results. So how do you choose the right pairing? Consider 4 key factors. 1. Is your sample type solid, liquid, powder, film, composite, isotropic versus anisotropic? 2. What are the required properties? Conductivity alone or conductivity plus diffusivity plus specific heat? 3. Is precision or speed more critical? Steady state for accuracy, transient for fast results. 4. What is the sample geometry and heat flow direction? Through plane, in plane, bulk, thin layers. Evaluating these factors helps ensure the method and module setup truly reflects how the method behaves in real-world conditions. Testing modules and testing methods each play distinct but complementary roles. Modules provide the physical environment and interfaces needed for testing. Methods provide the scientific framework that defines how heat is applied and how properties are calculated. When paired correctly, they deliver accurate, reliable thermophysical data. When mismatched, even the best instrument can produce misleading results. By choosing the right module and method combination, engineers and researchers can improve accuracy, reduce development time, and gain confidence in material performance.